We now go into the depths of the proof of the small Simplices lemma and therefore of the excision axiom. The small Simplices lemma stated the following. Situation was that we had a cover of our space X by sets whose interiors cover the whole space X, and then the statement is that the U small simplices, or the chain complex of U small simplices, injects into the chain complex of singular simplices, inducing a homology isomorphism. And in the previous video on the excision, we already learned the basic idea behind this result. It was based on a subdivision procedure. And to formally define the subdivision procedure, we do construction first on singular simplices in a standard simplex. So we're looking at the singular chain complex of a standard simplex, delta Q. And inside that chain complex, there is a subchain complex of the affine singular simplices. So let C star affine be the subchain complex of affine singular simplices. I will explain what I mean by that. So what is that? Well, these are singular simplices, so maps from, say, delta P to delta Q that are affine linear. So such a sigma lies in, say, CP affine delta Q by definition if sigma of a typical element in delta P looks like that. So this is I to 0, lambda I, and now sigma Vi. So the map sigma is determined by saying where the vertices Vi go to. They go to Wi, and then the whole map sigma is determined by this linear relation. So these are these singular affine singular simplices, and it's quite obvious that if you take the boundary of such a singular simplex, such an affine singular simplex, it's again a linear combination of affine singular simplices. So therefore, we really get a subchain complex. So the differential in the singular chain complex of delta Q restricts to a map on the C star affine.
And P and Q, there's no requirement that one is larger than the other or so?
No, right now they're just independent.
Okay.
Yeah. Mm-hmm. And by a slight abuse of notation, we will write for such a sigma W0 up to WP, so indicating that sigma is completely determined by saying where the images of the VIs are. And it's a slight abuse of notation because we had that notation also for the standard simplex, and now it's a notation for a map, but I don't think it will create confusion. So to define the barycentric barycentric subdivision procedure. That's the main tool for the proof. We first define it now on that chain complex, on the C affine delta Q chain complex. And I need some further notation. So if we have a point in delta Q and such a simplex, P simplex, I can form a P plus 1 simplex, which I write as W sigma, and it's just given by adding this point W to the W0 up to WP. Right, so this is a P plus 1 affine singular simplex. And we also get a map of the whole chain complex. Also the chain complex C star affine of delta Q is a free abelian group on the affine singular simplices. So to define a map on this affine singular chain complex, we only have to define it on this affine singular simplices. So we define a map W underbar from CP affine delta Q to C plus 1 affine delta Q is the linear extension of the map above. So this maps sigma to W sigma. And this is the linear extension, so it's a homomorphism. And thirdly, for each affine singular simplex, we get the barycenter. So the barycenter of sigma is really geometrically the barycenter, so it's the weighted sum of the Wi's. Right, and it's really the barycenter, so if you have, say, B equals 2 equals Q, and you have for sigma the identity, then the barycenter is the barycenter of this standard simplex.
So physically, it is the center of mass.
It is the center of mass.
Simplex has constant density.
Yeah. And now we're in a position to define the barycentric subdivision on C star affine delta Q. So the barycentric subdivision operator is a homomorphism from CP affine delta Q to itself and you know the idea of such a homomorphism. The idea is that it makes somehow singular simplices, in that case affine singular simplices, smaller somehow. Let's call it BP. And it is defined inductively on the zero simplices. It does nothing, it's the identity. So B0 sigma is just sigma, but on BP, for P at least 1, it does the following. You take the barycenter of sigma and then look at this associated map that we just defined, which was just adding this barycenter point in front of an affine singular simplex. And we apply this to BP minus 1 of the boundary of sigma. And if you remember the heuristics that we had in the last video for the subdivision, you can really see it here. Because what we're doing is we're looking at the boundary of sigma, and now think of the boundary in a geometric sense, really the boundary. We apply the subdivision to the boundary, and then we have this center of mass, this barycenter in the simplex, and then we erect
like cones over the...
Yeah, we take the cones with respect to that point, barycenter point, and with respect to all the p minus 1 simplices that appear in the subdivision of the boundary. And we will look at this now again for, yeah, let's say degree 1 and 2. And then we will see that this is really corresponds really to this geometric intuition that we have about the subdivision.
And the good thing about this inductive definition is we needn't worry about the sign that's hidden in the boundary operator.
Yeah, that's hidden in the boundary operator, exactly. So let's look at the easiest case. Well, the easiest case is degree 0, but there nothing happens. Let's look at the case where something happens in degree 1, and I want to look at the identity simplex. So the identity simplex is an affine singular simplex. In our notation, we could also write this as V0, V1. And we have to look at B1 sigma. It should somehow divide our simplex into halves. So it's the barycenter of B0 of the boundary. B0 is the identity. So let's forget about B0. Let's just write the boundary here. The boundary is V1 minus V2. And adding the barycenter is just 1/2 of V0 plus V2. Wrong brackets.
Shouldn't the sign be the other way around? V0 minus V1?
No, it's this way. You drop first V0.
Ah, right.
And that's, yeah,
right.
no, it's that way.
The dropping index is the one,
yeah.
Yes, that counts, right.
Don't make me nervous.
No, never mind. Apologies.
All right, so the simplex in that case, sigma, is that simplex. So this is V1, this is V0, and then we have this midpoint here. And what we see here for B1 of sigma is this simplex, this half, and the other half is that. So the arrow just indicates that this is identified with the standard 1 simplex. Well, sorry, let me start again. The arrow indicates somehow this as a singular simplex. It's a singular simplex, it's a map from the standard simplex, and the arrow indicates where the first basis vector goes to. And this is how it looks like. And the signs are that this gets a minus and this gets a plus. But ignoring signs and orientation, it's just dividing this 1 simplex into halves, what we expect from a subdivision of a 1 simplex. Yeah, let's look at the case p equals 2 as well. Slightly more interesting. So, and again, I want to look at the identity simplex. which is now V0, V1, V2. So what is B2 of sigma? It's the barycenter of sigma and the associated map applied to B1 of the boundary. So B1 of the boundary, what's the boundary? It's dropping V0 minus dropping V1 plus dropping V2. Then we apply B1. So now you see we have already here 3 singular simplices. Applying B1 gives us, for each of these singular simplices, 2 simplices. So we have 6 singular simplices. The barycenter map just does something to each singular simplice, doesn't increase the number of singular simplices. So in the end, we end up with 6 singular simplices. And I won't write down all 6. Let's write down maybe one of them or 2. So barycenter, and now B1 applied to that gives, I have to think, so this would be, yeah, 1/2 of V1 plus V2, V2 minus 1/2 V1 plus V2 V1. Well, and then I won't write the rest, but I will write the barycenter, so at least this very first simplex that we get. So we have 1/3 of V0 plus V1 plus V2, 1/2 of that sum, V2. And let's skip the other 5 singular simplices that we obtain. Let's just look at the picture now. What is that simplex? So the 6 simplices that we get, we had this maybe a bit bigger. So I'm just drawing a standard 2 simplex now. Sigma is a map, but since it's the identity, it's enough to draw this just the target space. And here's the barycenter of the sigma. Then the barycentric subdivision on the boundary does that. It just divides everything into halves. And then we end up by 6 singular simplices whose images you see in that picture. And the very first one that we actually wrote down is the one, so maybe I should draw here. Sorry, you can skip writing sigma. Sigma is the identity, so this is V1, this is V0, V1, V2, and the simplex that we see here is this one. Okay, and as Holger said, the appropriate signs we just get from the signs of the boundary operator, but it is a sign with coefficients plus or minus 1 of these geometric 6 simplices that you see here. That's the barycentric subdivision in degree 2, and then it goes on. If you have a tetrahedron, which is a 3 simplex, then you do to each 2-dimensional face, you do this procedure. You get lots of 2 simplices, and then you take the barycenter of the tetrahedron and erect all these small tetrahedra. So you cone off these 2 simplices in the tetrahedron.
Yeah, so the important thing to remember is that barycentric subdivision does not just mean you take the center of mass, this barycenter, and you connect it to the vertices of the simplex. It's way more than that. This iterative procedure says you get way more new simplices because you're doing it iteratively with respect to the faces. So this has the effect that actually the number of simplices after n times barycentric subdivision grows factorially, right?
Yes, it's factorial. And it's important to do that inductively. I mean, there are other ways to define a subdivision procedure that in some way makes the singular simplices smaller. The diameter of the singular simplices smaller. But the reason we have to do it that way is that we want that this barycentric subdivision operator that we defined formally here, we want this to be a chain map. Claim 1. B star is a chain map. And that's the advantage of this inductive definition. That's actually now quite formal, quite almost tautological to show. Nevertheless, let's do it. The proof goes, no surprise, also by induction. So by induction, we show the relation at the boundary of BP sigma is BP minus 1 of the boundary of sigma. So P equals 1. There is nothing to prove because the right-hand side is 0. So we, if you want, can formally define B minus 1 by 0. And the boundary of a zero simplex is also 0, so both sides are 0. So let's do the induction step. So let sigma be an affine singular P simplex in this complex. And before I really do the induction step, let me ponder about the following relation for a point in delta Q. I claim that for a point we have the following relation. So that's sigma minus this. And this should be W. And if you want, I could also write W underbar, because that was the way you define it on a singular simplex. Is the same as W sigma. So let's call this relation star, and let's ponder about it for a second. What do we do here? So sigma is this W0 up to WP, and then what this does is just adding the W in front. Now you take the boundary of that. So what happens? Boundary is subsequently dropping these points. The very first that gets dropped is the W that you inserted here, right? And this gives you back the sigma. What you then drop are these vertices W0 up to WP, but you still have this W added in front. So what's left is really minus W applied to the boundary of the sigma.
Yeah, the minus sign is because now the first vertex W is taken out, right? So
yeah.
The other ones should be, it's more like W minus D sigma, but that's the same as minus
yeah.
W D sigma.
So hence, so let's just insert the definition of BP. It's the barycenter of sigma, the associated map applied to bp minus 1 of the boundary of sigma. Now I want to apply the relation star inside bp minus 1 of the boundary of sigma. So what's inside here? And then minus barycenter sigma applied to the boundary of bp minus 1 of the boundary of sigma. So this is then bp minus 1 of delta sigma. So we want to prove that we have the chain map relation in degree p. So this, what comes now should be 0, right? Why is it 0? Well, we have to apply the induction hypothesis. The induction hypothesis says that, so it's bp minus 1 of the boundary of the boundary. Yeah. So induction hypothesis applied, and of course this is 0. And this shows the induction step. So it's a chain map.
But as of now, we just proved it's a chain map of this chain complex of affine singular chains of the standard Q simplex, right?
Right.
So
we haven't even defined what it means
Yeah.
to have a barycentric subdivision on the singular chains of an arbitrary space.
Yes.
And that comes not as the next step, but it comes as the third step. Well, let's talk about the third step
Yes.
when it comes to the third step. But yes, right now everything we do is inside a chain complex associated with standard simplex delta Q. So the second claim is a claim that I only make, and I will not prove it, but I will give you, if you want, a reference. It's in the book by Bredon. Give you the reference. The reason I won't prove it here is that the consequence of that claim is quite obvious. So the claim is that the diameter of every affine singular simplex, so that the image of that simplex, therefore, in the linear combination given by bp sigma is at most p over p plus 1 of the diameter of sigma. Okay, so for p equals 1, that's just, we divided it into halves, it's clear. Also for 2 simplex, it's 2 over 3. It's also clear from elementary geometry. In general, it's an easy direct calculation that you can do. And I won't do it because the following consequence, I think, is quite obvious. Hence, the diameter of every affine singular simplex in the linear combination given by the k-fold application of bp. So let me write it out. So this is bp applied k times. Approaches 0. As k goes to infinity. Some more space. And why? Well, this is at most p over p plus 1, which is smaller than 0, to the k, times the diameter of sigma. So it approaches 0 as k goes to infinity. And that's quite clear from the picture that you saw, that this simplices get smaller and smaller by applying the subdivision over and over again.
And at most means if this simplex happens to be this identity simplex, then it's exactly this formula, right?
If it's the identity simplex, it's exactly that, yeah. That's yes. The third claim, it was actually the fourth claim, what you were asking before, but the third claim I want to make is that that chain map is homotopic to the identity map. It's chain homotopic to the identity map, meaning that if we apply this subdivision to a homology class, it doesn't change the homology class. And that's something we've seen. We've seen the idea in the previous video for degree 1. And we saw the boundaries that are necessary to ensure that the homology class is not changed. But even more is true, the whole subdivision operator is chain homotopic to the identity. To the identity on that chain complex of affine singular simplices in delta Q. And the proof is really very, very similar to proving that it's a chain map. It's induction. You write down the formula for the chain homotopy. I will write down the formula. I will not do the induction. It's as formal as the argument for the chain map. So define this chain homotopy H star. So it goes from, it shifts the degree by 1. And this is also defined inductively. H0 is just the zero map. In degree 0, the subdivision does nothing, so we don't expect that the homotopy, the chain homotopy, should do anything. So it's the 0 map, and HP of simplex sigma is the map associated with the barycenter of sigma applied to BP sigma minus HP minus 1 of the boundary of sigma. It's also easy to see inductively that the chain homotopy, I mean, if you look at HP sigma, and if you look at all the singular simplices that appear in that linear combination, they will all lie in the image of sigma. Something that we saw in the previous video in degree 1, that the chain homotopy gives you, in degree 1, it gives you a linear combination of singular 2 simplices, but these singular 2 simplices are not really two-dimensional. Their image is really in the one of the already given singular 1 simplices, and you can see that quite easily. So let's believe that claim. Go to what Holger already asked about. What about barycentric subdivision in general, not just inside delta Q? And here we will see an important trick that we also will see later on in the lecture. So we extend, as soon as we have these maps B star and H star on delta Q, we can extend it by naturality to all spaces. So there's not really additional work needed here. It's really a formal trick. But a formal trick that still might be surprising if you see it for the first time. So I'm tempted to write B star for whatever space I look at, but maybe it's clearer, since we define it now, to call it Bx. So that's the barycentric subdivision operator I want to define for a given topological space X. So it will go from C star X to C star X. And I only have to tell you what I do on a singular P simplex in X. So what can I do? So I'm saying by naturality, right? I want, what do I mean by naturality, I should say, right? So natural in X, so I get really functor. Now I was confused for a second whether I wanted to say functor or natural transformation. I think I want to say a functor between, from the category, no, sorry. I have the functor which is going from the category of topological spaces to the category of chain complexes. And I have a natural transformation given by this Bx stars that I'm going to define. So that's what I mean by natural.
But natural transformation, what's the second functor? Natural transformation from the singular chain complex?
I have one functor, but I look at two copies of that functor if you want.
To
right?
itself, okay.
Yeah, the functor given by the singular chain complex C star, and I have like natural transformation from that functor to itself, and that's the Bx stars. Yeah. So let me first write it down and then discuss it a bit further. So usually we write induced maps by induced map by F star on the singular chain complex, but now it's really good to be extremely precise. So let's look at the induced map by sigma and apply it to BP delta P identity delta P. All right. So the surprising thing, or maybe also the confusing thing about this, is that sigma has a double meaning now. So sigma is just a map, and as a map, it induces maps between singular chain complexes. So here, it's just a map, and we apply CP sigma, so the induced map on singular chain complexes. But at the same time, sigma is also a simplex. And that's the role the sigma has here. So here is just an element in C star X, basis element of the singular chain complex. And this double meaning is very important here. So why am I forced by naturality to define it like that? Let's discuss that. It doesn't explain why it works, but it at least explains that if I want to have something natural, I have no choice here. So that's a side remark. In blue, naturality enforces this definition. Okay, so we have here C star of, let's say now delta P, or let's look at degree P actually. Then we have sigma. Sigma is a map from delta P to X, and as such it induces this map here. Now here we have what we already defined, the subdivision operator. And this is here what we want to define, but naturality means this has to commute, right? Now, inside here, we have a specific element, which is the identity. It's a specific element, and the induced map by sigma maps it to sigma. So BPX at sigma is what we want to define. So this is the thing we want to define. But now we are forced by mapping this over there. So this is exactly what's here, BP of the identity. And then mapping it down to CP sigma is exactly what this question mark should be if the whole construction should be natural in the space X. So we are really forced to do this definition, and maybe let me complete this. So if you go this way, we get this. All right. So end of side remark.
So you're defining here the component of the natural transformation at the object X in the category of topological spaces.
Yeah.
So the diagram on the lower, in blue on the lower part of the blackboard, that's the naturality statement, meaning that the upper one is sort of the component at the topological space delta P, right? And on the lower arrow, it's the component at X. So the upper one is the component at delta P, the lower one is the component at X. And if you really plug into the definition the case X equals delta P, I mean, then the confusion is probably complete, but then it will turn out that this is exactly what
it's the same, because then for sigma we have the identity. So yeah, it's really an extension of BP. I only explained now why naturality enforces that definition. You still have to check that what you end up with is really a natural construction. So it's really a natural transformation. So that's okay. It's almost clear, but it's not what I formally prove. I just looked at what is enforced. So we do the same for the homotopy. Also, the chain homotopy will be defined in a similar way. So Hx star is also a natural transformation. It goes from C star x to C star plus 1x, exactly in the same way. At least a glimpse into a very important technique that runs under the name acyclic models in algebraic topology that I will not formally explain now, will come up at a later stage. But this idea that certain natural constructions on the singular chain complex can be defined by only defining them on a model space delta Q. And that's exactly what's happening here. Nevertheless, there are certain things that you really have to check now that we don't, which are not hard, but potentially confusing because of this abstract definition. And the facts are that we still have a chain map and a natural chain map. That Hx star is a chain homotopy to the identity. Also that just transfers via this definition. And Hx is also natural, and we'll need that. And the third statement is that something that Holger just mentioned, or we both mentioned, that B delta Q and H delta Q are just extensions, or just identical what we already defined. So the whole family Bx extends the previous definitions. And the third definition is that if you look at Bx of a singular simplex and Hx of a singular simplex, then these are chains, for whatever degree, are chains in the image of sigma. So this extension is somehow localized. And you see that, of course, from the definition. So let's look at the definition that's still here on screen. The definition of hxp of sigma. You see, you do something completely within delta q, and then you apply Cp plus 1 of sigma. And therefore, all the singular simplices that you get in this linear combination are singular simplices that lie, or whose image lies in the image of sigma. The same for bxp sigma. And if you like this formal stuff, that last statement is also enforced by just saying that it's natural. So you don't even have to have the precise definition here. Just by the statement that it's natural, you can think about it, this also falls. But you see it here directly. So these claims have to be shown, but all these claims are completely formal consequences of what we've done before. The most important, well, they're all important, but a very important claim is that this construction really achieves what we aim at. We need a construction, that's the whole point of this barycentric subdivision operator. We need a procedure that makes singular simplices small. And we want it in the sense that at some point they are U small with regard to this cover U on a given space X. So claim 5 is exactly the statement we need, that for any cover U that has this property, this topological property, that the interiors of the UJs, if they're not necessarily open, at least cover X. And for any singular simplex, so an element in SPX, there is some number such that if we apply this subdivision operator k times, so again, same notation as before, that's the k-fold composition of bxp, and we apply it to that sigma, then what we end up with is U small. So all the singular simplices are U small in a linear combination, so this is an element in CPU. So for any sigma, there is a k, but there might be different k's depending on which sigma we have, such that is true. So this is an application of what we already discussed and the Lebesgue lemma. What does the Lebesgue lemma say? The Lebesgue lemma gives us a number epsilon such that, and where do we apply this Lebesgue lemma? We don't apply it on X because the Lebesgue lemma is a lemma about metric spaces. X is not a metric space, but we apply it to the standard simplex. So there is epsilon such that any subset of diameter at most epsilon in delta p, and delta p has the standard Euclidean metric, and we need also a cover to apply this Lebesgue lemma to, and the cover is the pulled back cover U on delta p. It's contained in one of the subsets. Pre-image of Uj. Okay, so we have this space, subspace of Euclidean space, delta p, with the usual metric. On that space, you have a cover whose interiors cover the whole delta p, and this is just a pull back of the cover U on X.
So finally we use that singular chains are continuous maps, right? Because you're claiming that this gives, the interiors give an open cover again.
Yeah, here we definitely apply it. Yeah, we need the interiors, the pullbacks are open, exactly. So this is the epsilon that the Lebesgue lemma gives us, and for each singular simplex sigma we get such an epsilon. And now you can guess what the k is. The k is so large that all the simplices if you apply BP to the standard simplex, that the standard simplices are in diameter smaller than epsilon. That's the k we need. So let k be large enough so that every simplex in the k-fold application of BP to the identity simplex has diameter at most epsilon. And remember what BXPK of sigma is. It is applying the induced map CP sigma to that. And if that has diameter at most epsilon, then all the singular simplices lie in one of these sets, and then we apply sigma, and so they finally lie in one of the subsets uj. So exactly what we want to show.
But the order of quantities is important, right? I mean, this k has to depend on the sigma.
Yeah,
there will
the
not
k
be a
depends on
global
the
k
sigma.
in general that works for all simplices.
I mean, the larger the simplex is in its image, then the more often we have to subdivide the simplex. So let me just conclude by saying then every simplex of Bx pk sigma, which is, if you forgot, Cp sigma of exactly this element, is in one of the UJs. So many preliminary steps on our path towards the proof of the small simplices lemma, but now we're finally at the stage where we can prove it, and therefore also conclude the proof of the excision axiom. So let's jump into the proof of the small simplices lemma now. So there are two steps. Let's give this inclusion that we're looking at a name. Let's call it I star, just for now. Okay, we want to show that I star is a homology isomorphism. And we do this in two steps. First step is proving the injectivity of HP of I star, and then proving the injectivity of HP of I star. So let's start with the surjectivity. It's slightly easier. So surjectivity means that any cycle here is homologous to a cycle which is U small. That's what we have to prove. So up to boundary, so to speak, any cycle in C star X is a cycle in C star U. So let's look at a cycle. Let A be such a cycle in CPX. All right, so we need something in CU. What could it be? Well, we apply what we already know. So we know that at least for each singular simplex in X, we can apply the barycentric subdivision operator a certain number of times, and then it lies in CPU of x. So now this A is a finite linear combination of singular simplices. For each one of these singular simplices, there is a certain k, the k from the previous lemma, so the number of times we have to apply the barycentric subdivision operator. Just take the maximum of these numbers, so apply that often the barycentric subdivision operator to A, and then we land in CPU of x. So there is a k, so that B x B k-fold composition applied to A is in CPU of x. And of course, what we expect now is that A is homologous to that element, and that would prove the injectivity.
And first of all, it's again a cycle because we proved that it's a chain map, and chain maps map cycled to cycles.
It's right. In particular, it's a cycle. Yeah, of course, that's important. Yeah. And the homology class of both are identical. Why is that? Well, that's because the barycentric subdivision is chain homotopic to the identity. So we can write that HP of the class given by this subdivided cycle that's the same as HP of this chain map. Applied to the element A. Right? So that's the chain map induces a map on homology. So that's this map applied to A by, I don't know, I want to say functoriality. This is HP of this chain map k-fold composition applied to A, but we know that HP of Bx star is the identity because Bx star is chain homotopic to the identity, so it's the identity to the k, so it's just the identity applied to A. So this is just A, or I should say the homology class of A. And therefore, surjectivity holds. Right, so here we're using that Bx is chain homotopic to the identity. Let's go to injectivity and then we're done. Injectivity is slightly more complicated. So here we have to start with a cycle in CU star. So let A be now already from the start in CU star of x, or let's say in degree p, be our cycle. And then we apply to this class the map induced by I star, and then we suppose that it's 0, meaning that A is a boundary not in CPUX, but in CPX. So that's the statement. Or that's the situation we have to look at. So if it's a boundary in CPX, we have to show it's already a boundary in CPUX. And that's exactly the injectivity on the level of homology. So suppose it is a boundary in C star x. So suppose that there is a B in CP plus 1 with boundary of B is A. Now we have to manufacture somehow out of B element in CP plus 1 U of x that has the same property, that its boundary is A. Of course, what shall we do? We apply the barycentric subdivision operator to B. What else could we do at this point? So choose K as above. So choose K so that bp plus 1, well, bx b plus 1 applied k times to b is in cp plus 1 u of x. And we will see the boundary of that element here is not quite A, but nevertheless it helps to consider this element now. What we need is to have, unlike before, a more explicit look at the chain homotopy. So let W star x be the chain homotopy not of Bx star but of the k-fold composition. So what am I doing here? So we have shown that there's a natural chain homotopy of Bx star to the identity. That was the H star before. It's from the analogy to homotopies of spaces, we know that if you have a self-map that's homotopic to the identity and you apply it k times and compose it k times with itself, it still will be homotopic to the identity. And the same is true on the level of chain homotopies. So it's not surprising that the k-fold composition is, again, chain homotopic to the identity. Small lemma that we don't discuss further now, but you end up again with a natural chain homotopy of this k-fold composition. So then we have, now I'm just writing down what chain homotopy means. So apply this to B minus B, and this is this differential chain homotopy plus chain homotopy differential. So this is differential of W x, I hope it's P plus 1. Yes, it is. Plus W x P and the differential, and here there should be B. That's the chain homotopy relation for W x star. What do we have now? Should be easy. It's always suspicious if the lecturer looks at his notes when he says that something is easy, right? So what we get is, we want to look at the boundary of this element bxk p plus 1 of b. And see what it is. So let's take the boundary on both sides. Then the first term on the right-hand side cancels. And this is then the boundary of x b. So we have this. Then this is A. Right, this is also A. Therefore, let's bring A to the other side. We want to represent A as a boundary in the complex C star U of x. So this is definitely a boundary in the complex C star U, because bx p plus 1, k of b is in cp plus 1 u of x. And then we have minus the boundary of wx p of a. And I claim this thing here is also in cp plus 1 u of x. So what do we need to conclude that? What we need is, and that's why I said in the beginning that injectivity is slightly more sophisticated than surjectivity, we actually do need the naturality of W at this point. Because the A lies, or I mean all the singular simplices that show up in the linear combination A, they all lie in one of the subsets uj. And now you apply wxp to that. Then it also lies in uj. So that's a consequence of naturality. I said that before, that the fact that the chain homotopy hx and the map bx have this localized property that if you apply them to a singular simplex, then whatever you end up with is all lying in the image of that singular simplex, is a consequence of naturality. It didn't quite argue like that, and now we have this abstract, so maybe we can spend a minute to think deeper on that, but that's a consequence of naturality. And let me now just say that this is all we need, because now A is a boundary. So let me say by naturality, I will elaborate a little bit on that. This is a boundary of an element in CP plus 1 of U. Naming of that element. Okay, so that's the proof. Let's elaborate on that part a little bit more to finish this. So why is that? Well, this A is some linear combination of singular simplices, right? So we have here, I don't know, let's say I from 0 to n of some coefficients, lambda I times some singular simplices, sigma I, and the image of each sigma I is completely contained in one of these subsets uj. So let's write uj of I, because it's depending on the singular simplex sigma I. All right? So that's how A in general looks like. Now we apply this natural chain homotopy wxp. And I want to claim that whatever I end up with, linear combination I end up with, still has that property. And therefore, wxpa is in CP plus 1 u of x. Why is that? Okay, so let's apply wx to this. Again, it's linear, so we really only have to look at what happens to a singular simplex. So I want to argue that all these are in CP uji, really. The final statement, conclusion from that will be that this is indeed what we want. It is in CP plus 1 u of x. So why is that? That's naturality, as already said. And naturality applied to the inclusion of uji into x. So let's call this inclusion I of uji into x. Because then it looks like this. Here you have uji. Here you have the map induced by the inclusion. Into CPX. Here we have C plus 1x and the map WP of x. And again, here is the map induced by this inclusion. And here, and now I'm applying naturality of the chain homotopy. Here we have WP of uji. Right? Now, the simplex sigma I is in CPX, but it comes from the left-hand side. So it actually lies in CPJI, so it comes from here. And therefore, if we apply WPX to the sigma I, we can also walk around this diagram, this commutative square in that direction. So we apply WP, and whatever we have, and that's the only thing important here, we are in CPUJI and then go via the inclusion to CP plus 1x. So that's the final remark, that what I explained now is this innocent looking phrase by naturality, but it shows the lemma of small simplices and therefore excision.